Hello, everyone. My name is Yiheng Lin. I'm a first-year undergraduate student at Tsinghua University. The paper I will present today is titled Online Optimization with Predictions and Non-Convex Sources. This is joint work with Gautam Go and Adam Weirman at Caltech. To begin with, I'm going to use a few cartoons to illustrate the problem setting of online optimization with movement cost. Starting from point x0, a hidden cost function f1 is reviewed. The learner picks a point x1 and incurs both the hidden cost and the movement cost. The hidden cost is the function value of f1 at point x1, and the movement cost is a function of x1 and x0. Usually, the movement cost is some distance measured between two consecutive decision points. At time step 2, another hidden cost function f2 is reviewed. The learner picks a point x2 and incurs both the hidden cost and the movement cost. So is time step 3. So formally, we are trying to minimize the total sum of hidden costs and movement costs online without the knowledge of the future. Notice that usually xt is constrained to some feasible set ft, which is changing through time steps. To quantify the performance of different algorithms, we define the offline optimal cost as the minimum cost one may incur on the same sequence of hidden cost functions if he has the full knowledge of the future. And the compare ratio is defined as the supreme of the ratio between the algorithm cost and the offline optimal cost over all possible hidden cost function sequence. And a common approach used to simplify this problem setting is to absorb the feasible set ft into the hidden cost function by doing a value extension. Specifically, we set ftx to infinity if x is not in the feasible set. Notice that this will not affect the convexity of the hidden cost function if ft is convex. However, if the feasible set is non-convex, this will lead to non-convex hidden cost, which provides a motivation for us to study non-convex hidden cost. In the next few slides, I will introduce some applications of online optimization with movement cost, as well as the motivation of studying non-convex hidden cost. The first example is geographical load balancing. In this example, we are trying to balancing the load of the server farms at different locations in order to meet the demand as well as saving energy. So in this example, the decision point xt is a d-dimensional vector that represents the number of active servers at different server farms. And the hidden cost ft captures the delay cost and the operating cost of the servers, while the movement cost captures the transition cost of turning on and off the servers. This problem setting has been studied in many previous works. In this example, we may have non-convex hidden costs if the average cost of running each server decreases as the total number of active server increases. The second example is robotic planning. In this example, we are trying to train a robotic camera to broadcast a basketball game. So in this example, xt represents the location of the center of the screen. And we use the hidden cost function to encourage the camera to capture the object of interest, maybe basketball. And the movement cost penalizes the camera for moving too much between two consecutive time steps. In order to do this, instead of using the distance between xt and xt minus 1 as the movement cost, we instead use the square of the distance. This problem setting has been studied in many previous work. And in this example, we may have non-convex heating cost function if there are multiple objects of interest. The third example I want to introduce is convex body chasing. This is a special case of online optimization with movement cost. Starting at x0, convex body K1 is reviewed, and the learner needs to pick a decision point x1 inside this convex body K1 and pays the movement cost of the distance between x1 and x0. The same thing happens again for time step 2 and time step 3. So this is a special case of online optimization with movement cost because we can set the heating cost function to be the indicator function of the convex body KD. Although the problem setting seems simple, this is a very hard problem, and only until recently there are some breakthroughs on the compare ratio, but it is still linear in the number of dimensions. We will come back to this specific example later. We have seen that in general, online optimization with movement cost is a hard problem. But there are some works consider even a harder setting where the learner does not have the predictions of the heating cost function. The point we want to make here is that in many problem settings, no predictions means no constant compare ratio. And predictions is what makes positive compare ratio results possible. So formally, let me introduce online optimization with predictions. No predictions means the learner has to pick its decision point xt before the heating cost function ft is reviewed. In contrast, the problem setting we introduced before, where the learner can observe the heating cost function ft before picking xt, is the case when the prediction window has a size of w equals 1. In many applications, actually the learner can have a larger prediction window. For example, this is the case when the prediction window has a size of 3. In this case, the learner can observe the heating cost functions f1, f2, and f3 before picking x1. Online optimization with predictions have been studied in lots of previous works, and their results can be summarized in a form like below. Suppose the heating cost function satisfies some conditions, and the movement cost is given by some special form. Given a prediction window of less W, the compare ratio of some algorithm is some function of W. Notice that the compare ratio may have different decay rate with respect to W as W tends to infinity. The common thing is that they all converge to 1 as W tends to infinity. Although these results may be very useful for specific applications, a big remaining question before our work is, under what general assumptions does the compare ratio converges to 1 as more predictions are available? This is worth considering because not all instances of online optimization with movement costs can leverage predictions to improve the compare ratio. For example, we give a counter example. We show that convex body chasing is a counter example in our paper. So in our paper, we give 2 general conditions under which the learner can use predictions to improve compare ratio, making it converge to 1 as more predictions are available. The first condition is order of growth. The second one is approximate triangle inequality. So it is important to notice that these 2 conditions do not require convexity of the heating cost and the movement cost. So the order of growth condition puts a lower bound on the heating cost function. Specifically, we say this lower bound grows proportionally with the distance between x and Vt, where Vt is the global minimizer of the heating cost function. So as you can see from this figure, this means the plot of this heating cost function should not go into the yellow area. Notice that convex body tracing do not satisfy this condition because the indicator of a convex body KT will intersect this yellow area. The second condition is approximate triangle inequality, which is a weak form of the triangle inequality. For example, when the movement cost is given by L2 norm, we can set eta equals 1, which is the triangle inequality. When the movement cost is L2 norm squared, it does not satisfy the triangle inequality, but it can satisfy condition 2 because we can set eta to 2. So our main theoretical result states that under these two general conditions, there exists online algorithms whose expected cost converge to the offline optimal cost as more predictions are available. Before introducing our algorithm, I'm going to introduce a similar approach, which is proposed in some previous works, and it is an important benchmark in the literature of online optimization with predictions. This is called fixed horizon control. At time step t+1, we use the predictions of heating cost functions ft plus 1 to ft plus w to compute a subsequence of decision points xt plus 1 to xt plus w and commit our decisions to this subsequence. This means we have nothing to do until the next time step t plus w plus 1, and then we compute another subsequence of decision points. Notice that this is how a subroutine of SFHC works. And depending on at which time step we compute the decision points, there are W different subroutines of SFHC. And by combining them together, we can obtain an algorithm which has a compare ratio that converts to 1 as more predictions are available. This works in many applications and problem settings. So the algorithm we propose, synchronized fixed horizon control, is very similar to SFHC, but the key difference is that we solve the subsequence xt plus 1 to xt plus w subject to the constraint that xt plus w must equal to Vt plus w, which is the global minimizer of the heating cost function at time step t plus w. We call this time step t plus w an anchor step. To see why this anchor step is important, we can think about the simplest case when the prediction window is of size 1. In this case, SFHC simply picks xt equal to Vt, which is the global minimizer of heating cost function ft. Although simple, we can show that this provides a constant compare ratio under the two general conditions we give. In contrast, SFHC picks xt to minimize the sum of the heating cost and the movement cost at the current time step. It turns out that, however, this stepwise greedy approach does not provide a constant compare ratio. And when more predictions are available, we do not need to restrict ourselves to picking the global minimizer of the heating cost function at each time step. So we can fix the head and the tail of the subsequence xt to xt plus w and optimize the decision points in the middle of this subsequence. We call the head and the tail of this subsequence anchor steps. So formally, SFHC subroutine edge solves the optimization problem subject to the constraint that xt equals to vt at anchor steps, where the set of anchor steps is decided by the remainder of time set t mode by the prediction window size w. Our theoretical result states that the average total cost of all the subroutines of SFHC is upper bounded by where it converges to the offline optimal cost as more predictions are available. However, this is not a compare-ratio result yet, because the average cost of the subroutines is not equal to the algorithm cost. We still need to figure out a way on how to combine these subroutines together. The first method, which is a common method used in many previous work, is taking the average of all subroutines. This works well for convex heating costs and movement costs. However, it does not work in the non-convex cases because Jensen inequality does not work for non-convex functions. So we can also use a simple example to see why. Suppose we have two subroutines. The first subroutine suggests that we should pick the red point on the left as the decision point, while the second subroutine suggests we should pick the right point on the right. So we decide to pick the average of them, which is the yellow point. But the yellow point xt has a huge heating cost. So as an alternative, we propose a randomized approach, which uses only one routine, but select anchor steps randomly. We show that this works for both convex and non-convex heating costs and movement costs. To see how it works, suppose currently we are at anchor step T1 and want to decide the next anchor step T2. We generate this interval T2 minus T1 uniform randomly in a range. And in our paper, we show that this method has an expected cost that converges to the offline optimal cost as more predictions are available. In conclusion, well, many previous work study online optimization with movement costs, study how to leverage the predictions for specific instances of online optimization with movement costs. Our work instead focus on answering under what general conditions do prediction help in online optimization with movement costs. We give two general conditions. The first one is order of growth, and the second is approximate triangle inequality. These two conditions are sufficient, and they suggest that convexity is not a necessary condition of leveraging the prediction window efficiently. Further, our algorithm SFHC gives the first compare-ratio result for non-convex online optimization with predictions. At the end of my talk, I want to acknowledge the co-authors of this paper, Gaosen Go and Adam Weirman. My name is Yiheng Lin. Here are our references. Thank you for listening.